Okay. Oh my god. Sorry. Here we go. Found it. Oh, jeez. Alright, so this is the practice set 2. And you got the practice set 8 and 9, right? We kind of ran through this because it wasn't that difficult. Two figures are congruent if you can use a sequence of rigid transformations. What are the rigid transformations? Rotations, reflections, and translations, right? So if you can use one of those transformations to move one exactly on top of the other one, then the two shapes are congruent. Let's look at the first one. Reflect figure A over the x-axis. So if you reflect figure A over the x-axis, then label the image. Well, it's easier if you, well, so yeah, I know figure A. So let me call this point C, point D, point E, point F. All right, so if you do that, it helps. I don't know why I do this. Over the x-axis, so we're going this way. So here's point C. Point C as best as I can. That's point C prime. This is D prime. This is E prime. And F prime would be around here. So C prime, D prime, E prime, F prime. So hopefully I did this correctly. So, okay. And then reflect figure B. So this is called B over the y-axis. Oh my god. So we're moving this and we're rotating, we're reflecting. So, and then from here to here, here's F. That would be F double prime, right? E would be somewhere over here. E double prime. D would be over here. D double prime and C double prime. So they're asking us, are A and C, are A, and let me highlight that, is this and the second image congruent? Well, it is. It doesn't matter. So let me show you something here. So if I took this triangle, right, and I did a translation. Let me move it. So let me actually make a copy here. Copy. Okay. So if I took that triangle, oops, duplicate, I mean. All right, so now there's two. No, there's still one. Sorry, duplicate. Carry part of duplicate. There we go. So, right. So let's say I took the original triangle, right, and I translate it. Are they the same? Yeah, of course they're the same. What if I rotate this? Let's see if I can rotate this, please. Ooh, now I rotated it. Are they congruent? Is it still the same exact triangle? Yes, it is. Right? So, and even if I reflected it, which I don't know how to do with this, right, where this triangle flips to the other side, or let's say reflected over horizontal line, right, so let me, and then let me reflect it, right, so I translated to the right, and then I reflected over a horizontal line, and is this original triangle and the second, and its image, the same triangle? Yes, they are. Okay, because it went through, we use rigid transformations, we use the translation, rotation, and reflection. As long as you only use those three, the original image, the pre-image, and every image after that will be the same. Here's a pentagon, ABCD, where it is, and then it was rotated 9 degrees. Wait, do I have a pentagon here? Please tell me I have a pentagon, and I do, right here. Look, pentagon. 1, 2, 3, pentagon, 5 sides, and we're gonna rotate this. Ooh. I can't tell the rotation, but I'm gonna rotate this. Are they congruent to each other? Of course they are. Nothing changed. The size didn't change. The angles didn't change. It's just in a new position. So which of these 4 multiple choices. Pentagon ABCD is not congruent, so that's obviously a lie. The area of pentagon ABCD is not equal. No, it is equal. It's the same pentagon. The angle measures of pentagon ABCD, A prime, B prime, C prime, D prime, E prime are congruent to this corresponding angle. So I'll make a duplicate here. Duplicate. Right? So here was the original pentagon, and now I came here, and all I did was turn it. Right? No, maybe that's not it. You know what? Instead of a pentagon, I'm gonna. Well, you get the idea, but I'm gonna use a triangle because this one you can't really see. So right here, let me use a triangle. So here's the triangle, and then so instead of a pentagon, just imagine it's a triangle. Duplicate. So if I took that triangle, rotate it 90 degrees clockwise, is that what it says? Counterclockwise, so we're rotating this way. Sorry, we're rotating this way. Is it still the same triangle? Yes, it is. Everything is the same. The corresponding sides are the same. This angle and this angle is the same. This angle and this angle is the same. This angle and this angle is the same. Determine where figure A is congruent to figure B. Well, is figure A congruent to figure B? Well, if you could take a tracing paper, and I hate saying that, if you take a trace paper, let's say you trace this. You know what? I'll trace it. I can trace it. Clear objects. Actually, I can trace this. So, if I went like this, right? So if I had tracing paper, which, oh, look at that. I do. And I took this tracing paper, right? Here's a triangle. And can I do something to this triangle? Right, I can, but so one of the things that I can do here is we can take the triangle, translate it down, and from here, right, it's right here by the way, we can find a horizontal line of reflection, vertical, right, we can imagine one right here, where it's the line, the mirror, the line of reflection will be right here, and if you reflect it, right, reflect over the line, you would get triangle. So, is A and B congruent? Yes, it is. How about these guys? Yes, here's your line of reflection. Imagine that's a mirror. This point here would be this point, and then I'm going to change colors. That point over there would be that point on the other side of the mirror. This point would be this point, and this point over here would be this point. Right, everybody is on the same distance away from the mirror. Every single, imagine those are 5 guys, 4 points, four guys. Everybody be equally distant from the mirror. It was a refraction, which is a rigid transformation. So because that is true, they all remain the same. So here, hopefully you can see that it is not congruent. Why? Because it's not the same objects here. This trapezoid here is 1, 2, 3 units, right? The base is 3 units, and if you count here, it's 1, 2, 3, 4. It's not even the same. It's not congruent. What about this guy here? Is it? It looks congruent. It looks like a rotation. Again, let me trace it, because by tracing thank you technology, take this guy over here, and I can rotate it. Ooh, let's rotate it. Rotate, and then if I rotate it and I put it right on top, oh, look at that. So those are rigid. They're congruent. Their side lengths are the same, the angles, everything's the same. Spiral review. What's a spiral review? A reflection over the x-axis. Okay, so this is something we definitely have to do a little bit more. So here is my y axis. Quadrant 1, quadrant 2, quadrant 3, quadrant 4. And we have a point 2, 5. So 2 to the right and 5 down. 1, 2, 1, 2, 3, 4, 5. So it's about here, right? 2, comma, -5. So what happens to this point if I reflect it over the x-axis? So it's going to go from here, it's the x-axis, over here. right? So imagine you are this orange point and you're sitting in front of this mirror, which is the x-axis. How many steps are you away from the x-axis? You're 5 steps, right? So we'll, on the other side, 1, 2, 3, 4, 5. 1, 2. This would be your image on the other side. And where's your image? Well, if you think about it, it didn't move left and right. So you're still on x, right? The coordinate is 2. But are you on the negative 5th floor? On the y-axis, are you on negative 5? No, you're not. You're on the positive. So when you reflect a point over the x-axis, first, so let's say you had x and y, a point that we don't know, and I said reflect that over the x-axis. You know what's going to happen? X is going to be the same, and whatever y is, we're going to negate it, which means it's going to be the opposite. So that's the rule for reflection over x-axis. If you can remember that. Reflection over the y-axis. So let's take that same point and let me change it. Now, if you think about it, this guy here, the orange guy, is 2 units away from the mirror. So on the other side, he would be 2 units away from the mirror as well. But he's not at 2 anymore. He's at negative 2. Up and down, did he go anywhere? No. We didn't change anything on the y-axis. So he's still on negative 5. So over the y-axis, let's see what happened. Look at your point. You had a point xy, right? So your xy, did anybody stay the same? Yeah, your y stayed the same. But what happened to your x? Your x changed. Your x went from positive to negative. So whatever your x is, his x is going to be this opposite. So that's a rule for reflection over the y-axis. That was 8. No, I'm not doing that. Let's look at practice set 9. Again, 8 was a little bit too simple. Let's find 9. That's 9. Okay, so let's do 9. All right, so 9. Here are 2 ways to determine whether 2 figures are congruent. 1, if you can determine a sequence of transformations that move one exactly onto the other. So if you can figure out which transformation, reflection, rotation, or translation was used to move one exactly on top of the other one, then it's the 2 figures are congruent. You can determine that all corresponding sides have the same length and all the corresponding angles have the same measure. Okay, 2 figures are not congruent. So if that happens, then they're both congruent. 1 second. So if you look at this image over here, right, congruent, notice that corresponding sides, and I'll use a highlighter here, this side over here and this side are 6, right? And if you look at the top one, that's 2, that's 2 corresponding. So if you were to cut this and put one trapezoid on top of each other, they would be exactly on top. I look at the angles. This is 45 degrees. This is 45 degrees. That's 45 as well. That's 45 and so forth. Now notice this one. Is there any differences? Well, right off the bat, you can see that this is 4 and that is 5. They're not the same. So it's just not congruent. So I don't even want to say anything else. Lesson practice. Determine whether the figures are congruent and explain how you know. Are they? Okay, do they even look alike? Okay, they're not congruent because you can see the length here. All right, if you look at the length of AB, which is this guy, right, that length, is that even close to what EF is? I mean, done. Right, they're not even the same. One is 4 and the other one is 3. So you already know they're not congruent. The corresponding sides are not congruent. Right, they must be the same size. This one, are they congruent? Oh, shoot, why did they make this? So, Mercury. This is looks like a rotation of 90 degrees, right, clockwise. So you can see that this rotated to that. Point C is this point over here. Point C was pointing that way, and now it's pointing this way. So definitely a rotation of 90 degrees. You can compare some length here, KJ and AB are the same, JI and FE are the same. You can look for other um, other lengths that are the same. Okay, again, triangle ABC and triangle XYZ are congruent. So they're saying these are congruent. So if they're congruent, then corresponding sides and corresponding angles are the same. Which sequence of transformations will move triangle ABC to XYZ? Let's see, how would you make this move here? Well, let me put an arrow. So if I put an arrow here, right, it's pointing that way. That part is this way. So definitely a reflection, right? Because C, which is Z, right, point C, this vertex here. So C is pointing that way, right? So if I were to make an arrow, right, on that line, it's pointing to the right. Now it's pointing to the left. So there's definitely a flip, right? So a reflection over where? Oh, a reflection over the y-axis. So that's something that's happening. So here, reflection over the y-axis, check. Reflection over the x-axis, garbage. D, reflection over the x-axis, garbage. So A or C looks good for now. And then after you reflect, so after this triangle moved to the other side, guess what? It went up. So I hope you can see that this triangle here, and then I'll do the translation. I'm not going to do a perfect translation, but so it moved. So if you translate, okay, it would first come here. And that's what do we do after that? We moved up how many? 2 points. So A is the correct answer. So are they congruent? Yes. If two rectangles have the same period, will they always be congruent? All right, so let's pick one. Let's pick something easy. Let's make this 3. Let's make this 5. Let's make obviously this 5 and this 3. Are they going? So what's the perimeter? Well, the perimeter is the distance around this shape. So 3 plus 5 plus 3 plus 5 equals 18. Let's pick another rectangle that has total of 18. Let's see, 5 and 5. No, this is 16. Sorry, 16. 2, 16, 2, 2, 6, and 6. 6 plus 2 plus 6 plus 2. Notice that this is also 16, right? It's the same perimeter. 2 plus 6 is 8. 8 plus 2 is 10. 10 plus 2 is 6. So it's 16. This is 16. So what do you think now? If two rectangles have the same perimeter, and they do, will they always be congruent? Absolutely not. I just proved it to you that they will not always be congruent. Right? In order to be congruent, the second triangle has to be a 3, 5, 3, 5. Okay? So the statement, if two rectangles have the same perimeter, which this one had, are they congruent? No, they're not. What in the world is this? Label figure ABC so that it corresponds. All right, so imagine that I rotated this. How would you label? Well, this would be A prime. Okay. This would be B prime. This would be C prime. This would be E prime. And where's D prime? D prime would be a little bit above D prime. If segment AB, this guy here, is 2 centimeters, how long is AB, A prime, B prime? It's also 2 centimeters. If all I did was rotate, reflect, or translate, the side lengths will always be the same. Okay? Plot point P prime, D prime, where you think is located. Well, D prime is going to be over here. Okay, Okay, explain your thinking. It's on the other side. It's a rotation. Okay, so if you gotta imagine this rotating, this guy over here, this ice cream cone rotating. So if this is rotating, right? Look at the figure. A is coming this way. D is also rotating, right? And then we have, what is this? Spiral. Okay. A rectangular room has a length of, let me draw it out. Always draw it out. Has a length of 12, length of 12 and a height of 15. So 12, 15. Let's leave it like that. A contractor creates a blueprint in the room using a scale factor of 1/6. Determine the length and the width of the room in the blueprint. So 12 feet. And then you have, this is the actual, right, in real life, actual. Scale factor. So we're going to draw it up. And we're going to use a scale factor of 1/6. So what that means, it means that going this way, right? Well, first of all, the scale factor is less than 1, so we know it's going to be a reduction. So let's multiply it. 15 times 1/6, 12 times 1/6, and get the two new dimensions. So 15 times 1/6. 3 divided by 6 divided by 3 is 2. It's 5. 5 over 2 is 2.5. So on the picture, this would measure 2.5 inches or something. 2.5 feet. And then this guy here, 12 times 1/6. 12 times 1/6 would be just 2. So after using a scale factor of 1/6, what is 1/6 of 12? This would be 2. So after a reduction, you would get that the blueprint would have a measurement of 2 feet going this way and 2.5 going up. How does the perimeter of the actual room compare to the perimeter of the blueprint? Oops, I need the picture back. Well, if you look at the perimeter of the original one, it was 12, 15, which means this is 15, this is 12. 15 and 15 is 30, plus 24 is 54. So the original perimeter is 54, and after the reduction, what's the perimeter? Well, this is 2, this is 2.5, let's add up the size. 2.5 and 2.5 is 5. Plus 4 is 9, so it's 54 and 9. So the perimeter of the actual room, well, compare 54 and 9. 9 to go to 54 is times 6, so the actual room is 6 times bigger than the drawing over here. Okay. How does the area of the room? Well, what's the area of a room here? 15 times 12, let's figure out. 15 times 12 is, the area is the space inside. 15 times 12 is 180, so the area of the original, right, is 180 feet squared. And then this one, if you multiply 2.5 times 2, the area is 5. So if you do 180 over 5, you get 36. So the original area is how many times bigger? It is 36 times bigger than the drawing we did with a where we use a scale factor of 1/6. That's it.